For that, here is what we are going to do. Once again, we are now going to parameterize this x. Yeah. Earlier we had this, right? We had said x was x star plus alpha v. Now we are not very happy with this, so we need a different kind of a parameterization. So much more general parameterization. So let's say we move from this and we say now we're going to talk about this x, and we're going to say this is x as a function of alpha, which is a parameter. I want you to appreciate that this one still falls within this as a special case. So whatever we have considered thus far still works. It's still accommodated within this new framework, a wider framework that we are trying to develop now. But this is a very special case of this. Yeah. Okay. Now let's go up to our usual tricks. That is, if you have f of x, that's essentially f of x of alpha. What is the job of this alpha? What is the job of this alpha? The job of this alpha is to keep meeting those constraints, right? So Hix is equal to 0 for I belonging to the set 1, 2, ... till m. Yes? By playing around with this parameter alpha, I am saying that I am not going to let you travel in any arbitrary direction, but only those directions along which you will preserve these equality constraints, so that you are remaining within the set D, because now your set D is characterized entirely by these equality constraints. Yes? So that is the special case we are making for this, that we can actually tangibly characterize this D. We are not just going to draw some arbitrary D and say, oh, this is my set D. You see, there is a big difference here. Every time you are invoking an equality constraint, you are cutting the dimension of the space in some way, no? If I give you an inequality constraint, say for example in R2, if I just say that x1 is greater than 0, it's a half space. It seems smaller than the original space, but structurally it's very much like R2. It's just one half of R2. On the other hand, if I give you an equality constraint, it looks nothing like R2. It's a very small, thin set of R2. It's actually a one-dimensional subspace of R2. So equality constraints are nice that way, right? So I want you to appreciate that through this formulation, we are not actually addressing the question we had a while back, which was this kind of a situation. This is not an example of something that can be characterized by an equality constraint, you see. This part might have some equality constraint, but at least this part cannot be fit into an equality constraint kind of a setup, right? So we are not really addressing this. It's important to know what we are addressing and what we are not. Okay, so now we do this kind of a thing here. Yeah. By the same token as previously, let's just introduce this G. Yes. So G of alpha we define as f of x of alpha. Okay. If you flip through the pages of your notebook and go back to the first lecture perhaps, where we introduced this G of alpha and then derived conditions therein, can you now tell me what does this lead to in terms of G if you are trying to optimize? What condition should you still satisfy? Of course, one of the things I need to mention here is that x at 0 is x star. Great, no? That's what would meet this as well, right? So as the parameter alpha is made 0, you are exactly at x star. As you keep varying alpha, you keep traversing along feasible curves or feasible constraint sets, or feasible directions in the constraint set. feasible points on the constraint set. That's what's characterized by this. Now, based on this understanding, what can we say in terms of G? Does it change one bit in terms of G? The argument in terms of G remains still the same, isn't it? I mean, you write G of alpha in a Taylor series expansion as G of 0 plus alpha G prime 0 plus higher order terms. Nothing changes. Yeah, this remains still the same. So the condition for minimality in terms of G should also remain the same, right? So we would also require once again that this must be equal to 0, exactly. The moment we have G prime 0 is equal to 0, we have to translate it back in terms of F. And what does that lead to? Based on this equation here, again you have to use chain rule. There is no explicit characterization of X alpha such as this. So what is the rule then? G prime alpha is equal to, once again chain rule, right? So first you differentiate F with respect to X. X is basically an n tuple, so it's grad of F dot product with so it's basically the term by term derivative of X with respect to each of the X n tuples in the X, X1 with respect to alpha, followed by X2 with respect to alpha, followed by X3 with respect to alpha. They are all parameterized in terms of alpha. Yes. So we write it as right. This leads us to this step. Now then, if this has to be true, based on this and this, what should be true then? Grad of F at x0, x0 is, it's got a name, it's x star. So this means dot product with, right, this must be but now we no longer can say that, unlike earlier, that this grad must vanish. It's a dot product that has to vanish. Yeah. What does this mean? What is, I wonder, the interpretation of, or maybe blue here, what is the interpretation of this term? What do you think? No, forget about the dot product. I'm just asking about the term I have circled here in blue. What is the interpretation of this term? Yeah, rate of change. Geometrically, whenever you have such questions, just think about one dimension, x as a parameter, represented as a parameter alpha, in terms of a parameter alpha. Yes, it's a tangent, right? It is a tangent. Do you all appreciate the fact that this is actually a tangent? Yeah. In other words, if I have x of alpha, I can also expand this in a Taylor series like so. Wouldn't you agree? So it's basically the linear approximation. It's basically the linear approximation of those x's, those curves passing through x star, of course, because at alpha is equal to 0, this fellow is nothing but x star, correct? So it is those curves which keep you within that feasible set, that is D, within the constraint set, yeah, and allow you to move along inside the constraint set. And if you just ignore these higher order terms, it's just the linear approximation. That's what the tangent tells you. So if you look at it locally, as if things are flattened out, and these incremental directions of traversal that are allowable, then that's what this x prime is telling you about. These are the tangents, right? So, yeah. So now let's get back once again. What is this saying? There's a beautiful geometric interpretation to this, and it fits in with what we already understand about this. You see, along a tangent, this fellow when projected along a tangent should not amount to anything. What does that mean? Locally, at least, if you can traverse along a tangent in one direction, you can traverse along its opposite direction. Now, if this fellow gets projected on the tangent along one direction and leads to anything but 0, when it gets projected along the opposite direction, will have an opposite sign. So, there is a direction, at least even incrementally so, along which you can do better in terms of minimizing the function. It's the same interpretation. Earlier it was all arbitrary directions because all possible straight line directions were feasible. Now you're just saying, oh, I'm going to now restrict myself to these tangents. These are the tangent space. So there's a particular name assigned for that. It's basically the tangent space at x star to this set D. Okay, this is a tangent space. But we want a nicer characterization of fellows that live inside this tangent space. How do we do that? Well, in order to understand that, we have to first figure out how are we characterizing this space D itself in terms of H. A tangent is a first order approximation of sorts, right, of that X. So, let us look at this. H I X alpha is equal to 0, isn't it? For I belonging to the set 1, 2, that is all the M constraints are met, isn't it? Now, if I were to take the gradient of this fellow, yeah, or if I were to differentiate this with respect to alpha, just like I did for this fellow, the f that is looked at it as a function of alpha through this dummy g that I cooked up. Yeah. Now, if I looked at this, what would turn out as a result? It's the same thing, right? Very similarly, I will also have it just follows from a straightforward differentiation with respect to alpha. Yes. Now, plugging in alpha is equal to 0 because I am concerned about the tangent space at x star. It's like a local, very small local kind of a tangent space. In fact, it's a subspace. Yeah, we'll see that shortly when we characterize this. Yeah, and that's what we are trying to do now with all of this. So at alpha is equal to 0, what happens? We have, of course, if you plug in alpha is equal to 0 here, you just get x star and its dot product with voila, this is the tangent direction. So how are the tangent spaces then characterized? Once you think about it, it's very obvious, intuitively at least. But this is the mathematical description. Yeah. So anything that's a tangent must satisfy the condition that it is orthogonal to the gradients of all those equality constraints at that point x star. Yes. So we have gotten a handle on how to characterize these fellows. I had marked it with blue, I believe, in the previous one. Yeah. You see here, anything that's a tangent must actually satisfy this. In addition, now we are going to invoke one more condition. Actually, we are going to introduce the definition of a so-called regular point, and you will see why it helps us. Okay. So, what is a regular point? I will not write the whole definition down, you can look up in the book, but the idea is that at x star, if grad hi x star I is equal to 1, 2, dot 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 till m is a linearly independent set, then x star is said to be a regular point. Kind of looks like coming out of nowhere, isn't it? Yeah, why suddenly this regular point? Let's look at the last thing we were seeing here. We are trying to characterize this. We said, or we've shown so far, that any point or any vector which claims to be a tangent vector must satisfy this condition. That's a characterization. But the converse is also true, provided the point is a regular point. That's the reason I introduced the definition of regular point. What is the converse going to look like? The base statement is any tangent vector must satisfy this. The converse would be any vector that satisfies this condition. So, in other words, if I have for any v satisfying where x star is a regular point. Let me get rid of the for here. Yeah, any v satisfying this is a tangent or belongs to the tangent space. So, it is both ways. I will not prove this rigorously, but I will just give you the intuition behind this. Okay. What am I saying here and why this regularity is important? Let us try and wrap our head around this. The first part I hope is clear, right? This is true just by dint of this fact. Now we are saying you pick out any vector and you check whether that vector is orthogonal to each of these gradients, and provided this point x star at which you are fixing up this tangent space is a regular point. Okay. What is the intuition behind this? What kind of situations arise if it is not a regular point? Let us take an instance of a situation where you do not have a regular point, and then you will perhaps appreciate why we are really hung up on this. Again, take this point x1, x2. Okay. Suppose you have a constraint which is like a parabola, which is a parabola in fact. Yeah. So, this curve may be written as h1x can be, what is this? X, yeah. This is x squared is equal to 4y. So, x2 minus x1 squared. That should be it, no? Is it? That is what this is, right? Let us take another constraint. Just x2. Okay. Let me use a different color to denote these two. So, this is your first constraint, ignore the red part that is visible below, and this is your second constraint, right? And focus on the point that is the origin here. what is grad h1 and grad h2 evaluated at the origin? Can you tell me quickly? This is partial with respect to x1 is minus 2x1, evaluated at origin is 0. This is 1. What about this? 0 of course, because it's not even dependent on this. This one is 1. Are they linearly independent? No. So origin is not a regular point here. What happens as a result? Why are we really so intent on this being a regular point? If you now look at a zoomed version of this, these two appear to be the same constraint. In a local sense, when you look at grad h and grad h1 and grad h2, they appear to be the same constraint. So if you have two constraints, yeah, then what happens? Two constraints that are identical. It means you essentially have only one constraint. In R2, if you have one constraint, you are cutting down the dimension by 1, so you perceive as if you have a freedom along one particular direction. Which direction would that be? Perhaps the direction that's orthogonal to this. So in the local sense, you perceive of this direction as a feasible direction of traversal. But quite clearly that is not so. In reality, in the global sense, there are two constraints. One constraint is already giving you a curve, which is like a one-dimensional object. The other is also like, it's a straight line in fact, so it is a one-dimensional object. The intersection of these two one-dimensional objects gives you a point which is a zero-dimensional object. So if you are already at that point, there is no way to traverse. There is no feasible path that actually exists in your problem in the global sense. But by localizing this, or by sort of looking at a local version of this constraint, you are under the misapprehension that there is actually in reality only one constraint, which is this. So anything orthogonal to this direction is as if a legitimate tangent direction. That's clearly flawed, right? So this is why when you are taking the gradient of this and looking at a local version of this, it is very important that the global picture and the local picture agree, and for that to be the case, you need exactly as many constraints in the local version, that is in the grad form, as in the original version, that is in the H form, for which you need the point to be a regular point. That's the reason why we were so intent on ensuring that, and so much so that we actually introduced the definition of this regular point. Because otherwise all this local thing, this squinting our eyes and zooming in on this small neighborhood around this point, x star, will not be legit anymore. So we need this regularity condition to hold true. If you have m constraints, the grads of those m constraints at that point should each pose a new constraint, so that you are cutting down the degrees of freedom by 1 each time you add one of those grads in your list of stacked up constraints, right. So locally it looks like an n minus m dimensional subspace. Why is that a subspace? Well, if you know the definition of a subspace, you would immediately be able to see why this is a subspace. And also getting back to the question of the converse being true. Now suppose you have a vector, it's after all finite dimensional space, right. Suppose you have a vector which is orthogonal to each of these m gradients. So it is in the orthogonal complement of the subspace spanned by m linearly independent vectors. So it is a vector that lies in an n minus m dimensional subspace, because the sum of the dimensions of a vector space and its orthogonal complement when you are living inside a finite dimensional vector space is equal to the dimension of the ambient space, which is n. So you have m constraints, each of them is linearly independent, and this vector v arbitrarily that you picked up, which is orthogonal to each of those m constraints. So it is residing inside the orthogonal complement of the span of the grad h's. Am I going too fast? Is that clear? How many grad h's are there? Exactly as many as the number of h's. How many of them are linearly independent? All of them, because it's a regular point. That's the assumption we will run with hereafter. So you have v satisfying m constraints V has degrees of freedom which is n minus m. So if you write it down in the form of a matrix Ax is equal to 0, it's exactly the linear system of equations. The grads will take up the grads evaluated at x star will give you constant coefficients. So it's basically m equations. Yeah, each of them adding a new constraint. The rank is full row rank. So there is exactly n minus m degrees of freedom. It's an n minus m dimensional subspace. So the tangent space is an n minus m dimensional subspace if you think of x star as your origin, pivoted at x star. So if you stitch them together, these are like your tangent spaces. Yeah, so you can keep moving them along this and you form a bundle. But okay, we will not get into that at the moment. The important thing here is, which we will derive in the next module or the next lecture, is that this has very, very grave ramifications, because this will allow us to go from a constrained problem to an unconstrained problem. Okay. How so? The idea is quite simple really. We have now characterized the tangent vector. It's an if and only if, at least we have justified within our minds that if a vector is orthogonal to each of the grads, it is a tangent vector. If a vector is a tangent vector, it has to be orthogonal to each of the grads. So it's an if and only if condition. Now we have also seen just a while back that this must be true for every tangent vector. So that means every tangent vector, which is in turn something that's orthogonal to all of those grads, must also be orthogonal to this fellow, right? That's from the condition of optimality. Yes. How to now bypass this description through this via this tangent vector route? Because it now seems that every time you find a tangent vector, along that tangent vector you take the dot product with grad f and it must vanish. So it is predicated on finding this tangent vector at every instant or on every successive occasion. How do we instead bypass this? We will see that this grad f will actually be a linear combination of the grad h's. Okay, so that we don't have to go via the tangent vector. That's what we shall see next, and that will lead us to something you might have actually been familiar with earlier in optimization course, to something called as Lagrange multipliers. So we'll introduce that in the next module. Thank you.